Today we're going to look at lesson 9.4, which is on linear, quadratic, and exponential models. In this lesson, we will compare linear, quadratic, and exponential models. Given a set of data, decide which type of function models the data, and write an equation to describe the function. So why learn this? Different situations in sports can be described by linear, quadratic, or exponential models. So we'll look at the tables below. The data shows three ways you have learned that variable quantities can be related. The relationships shown are linear, quadratic, and exponential. So for linear here, we're looking at training heart rate, the age, and the beats per minute, and then this is the graph. Remember, a linear graph will form a straight line. Quadratic, volleyball height, so time in seconds and the height. And volleyball height forms a parabola. And then exponential, it will increase or decrease rapidly. So round one and then the number of teams left in the tournament, it decreases pretty rapidly as the number of rounds go on because people get eliminated each round. So in real world, people often gather data and they must decide what kind of relationship, if any, they think best describe the data. So there might not be a perfect constant rate of change for our linear data here. So we have to just give the best description for that relationship. And the same thing with the parabola. It might not form a perfect parabola, but if it's taking that shape, which a volleyball should, because it goes up and then it comes back down as time goes on. So in example 1, we are going to graph the data to choose a model. So we'll graph the relationship given in the table, and then we'll decide what kind of model best describes the data. So I have my graph set up. My time I'm scaling by 1 for every 2 grid marks, and then 10 on the y-axis. So my first coordinate is going to be 0, 10. So right here, 1, 20, 2, 40, and then 3, 80. So then here, if I connect my dots, I have a curve that is going on here. So it's not going to be linear. Here, in this case, we can't really say it's quadratic because we don't know what's going on over here. But in this case, I would say that it is exponential. Okay, it appears to be exponential. So we're just picking the type that best matches the data. For B, we have Celsius and Fahrenheit, so we'll do the same thing. We'll graph and then describe what kind of model best describes the data. So for degrees Celsius down here, I'm scaling by 5, and then Fahrenheit I scaled by 10. Some of these I'm going to have to approximate a little bit just because not every single digit is counted for on my x and y axis. So 0, 32. So 0 and then 32 would be about right here. 541, and then 10, 50, 15, 59, and then 20, 68. Okay, so this is what my data looks like here, and that would continue. So in this type of situation, the data appears to be linear. It's forming a straight line. So now there are 2 check it out problems for you to do. You're going to graph each set of data and then describe what kind of model best describes the data. So go ahead, pause the video, and then resume when you're ready to check your answer. So for A, I have negative 3.3, so left 3, and then up about 0.3. So I scaled by 1 here. So it's going to be pretty close to the x-axis. negative 2.44, so a little bit closer to halfway there. And then 0, 1, so right here. 1, 1.5. 2, 2.5, 1, 2. And then 3, 3.38, so 3, 3.38. Okay, so that's about what my graph would look like. And if I would connect this, this is going to form something that looks like an exponential function. Okay, so we're going to say 1a is exponential. So now we're going to go ahead and look at B. Do the same thing, graph. My x-axis I scaled by 1, y-axis I scaled by 2, just because I have 2 coordinates here on my y, the y values that are bigger than 10, so I couldn't scale by 1. So negative 3, negative 14, so left 3 down 1, 2, 3, 4, 5, 6, 7 to get me to negative 14. Negative 2, negative 9, so left 2 down 1, 2, 3, 4, that gets me to 8, and down a half gets me to negative 9. Negative 1, negative 6, so negative 1, negative 6. 0, negative 5, so 1, 2, so about right here. 1, negative 6, so 1 down 6. 2, negative 9. And then 3, negative 14. So here, this forms, sorry, that was a bad job connecting there. This forms a parabola. So this is going to be quadratic. Okay, so you plot your points, connect them, and describe whether it's linear, quadratic, or exponential. So now we're going to go ahead and look at example 2. Another way to decide what kind of relationship, if any, best describes a data set is to use patterns. So we're going to look at tables and see what kind of pattern we have going on. So in A, we have height of bridge suspension cables, the cable's distance from tower feet, and then cable's height in feet. So before I get into these examples, there's a little note over here that's really important. When the independent variable changes by a constant amount, linear functions have constant first differences. So linear, constant first differences. Quadratic have constant second differences. And then exponentials have a constant ratio. So you're going to be looking at multiplication there. So in A, my feet here for the distance from the tower, that's increasing by 100. I'm adding 100 each time. So I have a constant rate of change of my x. So let's see if I have a constant rate of change over here. So going from 400 to 256, I need to subtract 144. From 256 to 144, I subtract 112. From 144 to 64, I subtract 80. And then my first difference didn't work, so it's not linear. So let's see if there's a second difference. So going from negative 44 to negative 112, I'm adding 32. From negative 112 to negative 80, I'm adding 32. So the second difference here is constant. So that means this is going to be quadratic. Okay, so second difference, constant, quadratic. For B, I have the age of the car. That's increasing by 1. Here, you could see that there's a relationship. You're multiplying to get the next value. You're multiplying by 0.85. So you could just take the ratios of those. You could do 17,000 divided by 20,000 to get that 0.85. Same thing for the other values. So you're just taking the second value, dividing it by the previous value, to get what you're multiplying by. So here we have a constant ratio. And since we have a constant ratio, that's going to be exponential. Now, when you do this, you can go through a process of elimination. First, you should always check to see if it's linear. So see if you're adding the same thing or subtracting the same thing each time. Here you're not, okay? Then I would check to see if you can see if it's multiplying. And if that didn't work, then I would go to your second difference. But you could go in order. You could see if there's a first difference, second difference, and then last check to see if it's a constant ratio. So you're kind of doing process of elimination to go through and decide if it's linear, quadratic, or exponential. So now there is a check it out problem for you to do. You're going to look for a pattern in the data set to determine which kind of model best describes the data. So I recommend putting this in a table first and then looking for a pattern. So go ahead, take a moment, pause the video, and then resume when you're ready to check your answer. So I'm going to set up an XY table. So we have -2, 10, -1, 1, 0, -2, 1, 1, and 2, 10. Okay, so first I notice that my x values, I'm adding 1. So there's a constant rate of change for my x values. Now I need to go see if there's a constant rate of change for my y values. Okay, so to go from 10 to 1, I'm subtracting 9, but I don't subtract 9 to get to -2. So it's not going to be linear. Then from there, to see if I'm multiplying by something, to go from 1 to 10, I would multiply by 1/10, but to go from -2, from 1 to -2, I'm multiplying by -2. So that's not going to be a constant ratio. So now I'm going to go look and see if I have a second difference. So let's find the first difference. So to go from 10 to 1, I'm subtracting 9. From 1 to -2, I'm subtracting 3. -2 to +1, I add 3. And then 1 to 9, or 1 to 10, I add 9. So that's my first difference. Second difference, from -9 to -3, I'm adding 6. From -3 to +3, I add 6. And 3 to 9, I add 6. So we have a second difference that is constant. So second difference is constant. So this is going to mean this relationship, the data set, is quadratic. So now we're going to go ahead and look at example 3. So after deciding which model best fits the data, you write a function. Recall the general forms of linear, quadratic, and exponential functions. So linear is in the form y equals mx plus b, where m is your slope, b is your y-intercept. Quadratic, you have y equals ax squared plus bx plus c. c is your y-intercept. And then exponential, y equals a b to the x. So in example 3, we're going to look at the relationship, figure out what's going on, decide if it's linear, quadratic, or exponential, and then write the function from there. So here, use the data in the table to describe how the ladybug population is changing. Then write a function that models the data. Use your function to predict the ladybug population after 1 year. So we're describing the relationship, writing a function, and then predicting the population after 1 year. So there's 3 parts to this question. So the ladybug population, 0 months, 10, 1 month, 30, 2 months, 90, 3 months, 270. So we are going to first look at the table and figure out what's going on. So going from 0 to 1, I'm adding 1, 1 to 2, add 1, 2 to 3, add 1. So I have a constant change in my x values. So now let's see if it's linear. To go from 10 to 30, I add 20. 30 to 90, I have to add 60. So that's not a constant first difference. Then I like to see if it's exponential. So to go from 10 to 30, I multiply by 3. 30 to 90, multiply by 3. 90 to 270, multiply by 3. So here we do have a constant ratio. Each time I'm multiplying by 3. So here, each month, the ladybug population is multiplied by 3. So the population is being tripled each month. And since it's being multiplied by 3, there's that constant ratio. So that means this relationship is going to be exponential. So now we are going to write the function. Since we know that it is exponential, y equals ab to the x power. So we have to figure out what a and b are. So we have a constant ratio of 3. Okay, 3 over 1. So constant ratio equals 3. So in this case, that means b equals 3. So now I'm going to go ahead and substitute that in for b. So I'm going to have y equals a, and then 3 to the x power. So in order to figure out what a is, we are going to choose an ordered pair from here, substitute it in for y and x, and go ahead and figure out what a is. So we can choose any ordered pair. So I'm going to choose 0, 10, just because it's the first one. So I'm going to substitute in 0 for 3 and 10 for y. So 10 equals a and 3 to the 0 power. 3 to the 0 power is just 1. So we're going to have 10 equals a times 1, which means a times 1 is just a, so that's going to mean a equals 1. So b equals 3, a equals 1. So now I'm going to go write my exponential function. So here, my exponential function, or I apologize, not a equals 1, that should be a equals 10. A times 1 is a, and a equals 10. I apologize for your notes. So let me fix that. 10. So let's try that again. I'm going to go write my exponential function now. So y equals a, which is 10, times b, 3 to the x power. So y equals 10 times 3 to the x power. So that is my exponential function. So now I'm going to predict the ladybug population after 1 year. Okay, so that means 1 year is 12 months. Because here we were talking about x in time of months. That means x equals 12. So I'm going to have y equals 10 times 3 to the 12th power. By order of operations, I have to do my exponent first. So I'm going to have 3 to the 12th power. And that's going to give you a pretty large number. So you're going to have y equals 10 times 3 to the 12th power is 531,441. So 531,441. And now you take that and multiply it by 10. So now you get 5,314,410. So your answer is 5,314,410 ladybugs. Now there is a check it out problem for you to do. So go ahead, take a moment, pause the video, and then resume when you're ready to check your answer. So it says, use the data in the table to describe how the oven temperature is changing. Then write a function that models the data. Use your function to predict the temperature after 1 hour. So my time in minutes, going from 0 to 10, I add 10, 10 to 20, I add 10, 20 to 30, I add 10. Now, in the bottom here, 375 to 325, I'm subtracting 50. 325 to 275, subtracting 50. 275 to 225, I'm subtracting 50. So I have a constant first difference. So I'm subtracting 50 each time. So we have a constant first difference. So this means this is going to be linear. Okay. So the temperature of the oven decreases 50 degrees Fahrenheit every 10 minutes. So that's what's being described. We're adding 10 minutes each time, but every 10 minutes it's decreasing by 50 degrees. So that's describing how the temperature is changing. So now we're going to write the function. So since it's linear, it's going to be in the form y equals mx plus b. So to get this, we have to look for our slope. Our slope is the change of y over change of x. So m is going to equal negative 50 over 10. And that simplifies to negative 5. B, our y-intercept, is when x is 0. So our b is going to be 375. So putting that together, my equation is y equals negative 5x plus 375. Then I need to find the temperature after 1 hour. And 1 hour, we're talking in minutes here, so this is going to be 60 minutes. So we're going to substitute in 60 for x. So we're going to have y equals negative 5 times 60 plus 375. So here x equals 60. So negative 5 times 60 will give you negative 300. And then add 375. And here we are going to get positive 75. So that means 75 degrees Fahrenheit will be our answer for that last part.